Good afternoon to the sixth day of Anla Communication Date Coaching classes. Today we will start our presentation with some of the questions asked, useful questions that are asked by students earlier. We will try to address these questions, and after that we will start the actual lecture session of today. So why AM is a non-linear method of modulation? Few students asked. Now I would like to clarify this question. So the general expression for AM is SAM of T means the modulated version of AM signal may be expressed as AC into 1 plus mu M of T cos 2 pi FCT, where mu may be K into AM. So I want to take two modulating signals, M1 of T and M2 of T. If these two modulating signals are generating two AM waves, let us suppose the first AM wave is AC into 1 plus mu M1 of T cos 2 pi FCT. Similarly, the second modulating signal generates AC into mu M2 of T cos 2 pi FCT. So these are the two signals, two AM waves generated by two different modulating signals or information bearing signals. So now when I want to generate the additive signal, that is, I want to add M1 and M2, thereby I will get a new modulating signal, that is M3, which may be expressed as M1 plus M1 of T plus M2 of T. So the corresponding AM waves also, we know that SAM1 and SAM2, these two will be added, then I will come out with AC into 1 plus mu M1 plus M2 of cos 2 pi FCT. This is the third AM wave. So unlike that, I want to add the first modulating signal and I want to add the second AM wave. And if I want to generate the AM wave generated by the third signal, that is the sum, straight away without adding the corresponding modulated versions of the signal, if I take the signal and then take up generate another AM wave, this is astonishingly AC into 2 plus mu into M1 plus M2 cos 2 pi FCT, which is different when compared to the signal which is generated by an additive signal. So therefore, the signal which is generated by additivity and the third signal AM wave equation are not equal. So therefore, as it is not satisfying additivity property, we can say that it is a nonlinear method of modulation, or we can also check for homogeneity. It is not required here. So therefore, as it is not being satisfying the additivity, so that is, when I generate an AM wave separately by two modulating signals, and if I add them, if I add the two modulating signals and generate the resultant AM wave, those two AM waves are not equal. So therefore, AM is not linear. In fact, to prove this for any method of modulation, for the case of DSBSC, you can take any DSBSC signal may be expressed as the modulating signal times cos omega CT, which is a product of the baseband signal or modulating signal and the carrier. Let us suppose M1 of T cos omega CT is the DSBSC signal generated by the first message, that is first message bearing signal or first modulating signal. Second modulating signal is generating XC2. Let us suppose this is the DSBSC wave, which is the product of M2 and the carrier cos omega CT. So I want to do the same additive, verify the additivity property of adding the two messages and then generating the corresponding DSBSC signal, which may be expressed as M1 plus M2 cos omega CT. So which is M1 cos omega CT plus M2 cos omega CT. When I add these two and also generate this as additive signal as a DS used to generate a DSBSC, I will also come out with the same result. Why? Because M1 plus M2 cos 2 pi FCT will be the result. M1 plus M2 cos 2 pi FCT will develop the same. So therefore, it is satisfying additivity property. That is the reason why this is a linear method of modulation. Not only this, all suppressed carrier modulation mechanisms, right from the double sideband suppressed carrier, SSB, VSB, you can verify this particular property. So therefore, AM is a non-linear method of modulation, whereas DSBSC is a linear method of modulation. And another student asked why FM is a non-linear method of modulation. In the same way, we will try to prove. We take a baseband signal M1 of t, another baseband signal M2 of t, means two messages that are taken. If these two messages are used in order to generate an angle modulated signal, let it be an FM wave or PM wave. Here, we have considered an FM wave, or we have considered the case of FM. Why? Because we want to prove FM is nonlinear. So with the baseband signal M1 of t is being taken as the message, the corresponding FM equation is AC cos 2 pi FCT plus 2 pi kf integral minus infinity to infinity m of t dt, as here m1 of t is the message. Similarly, for the second message m2 of t, we want to generate AC cos 2 pi FCT plus 2 pi kf integral minus infinity to infinity m2 of t dt. These are the two different FM waves generated by the two messages M1 and M2. Now we want to add these two messages. The additive message we want to use for generation of the same FM wave. Then the corresponding FM wave, if you can see, AC cos 2 pi FCT plus 2 pi kf M1 plus M2 into T. Why? Because this message we need to take it as the new message, the additive message, which will be M1 plus M2, whereas here I want to substitute that. So this FM wave is no way same as that of the FM wave that is being generated by the sum. If I sum up these two, AC cos 2 pi FCT plus 2 pi kf integral M1 of t dt, this is added with AC cos 2 pi FCT plus 2 pi kf integral minus infinity to infinity m of t dt. So therefore, definitely it is also not satisfying the additivity property here. The added signal will generate AC cos 4 pi FCT, AC cos 4 pi FCT plus 2 pi kf integral m1 plus m2 into t is the additive message generated FM wave. As if this is taken as 3 and this is taken as 4, then 3 and 4 are unequal. So therefore, FM is not linear method of modulation. The same you can prove it for PM also. Take the corresponding phase modulated wave. Let M1 of t is the message, first message, M2 of t is the second message. Corresponding PM waves, phase modulated wave, may be represented as AC cos omega Ct plus Kp into M of t is the standard expression. So as the first message is M1, A cos or AC cos omega Ct Kp, M1 of t is the first PM wave, and the second PM wave is AC cos omega Ct plus Kp into M2 of t. So the additive signal M1 plus M2 I have just taken, and then if the new signal is M1 plus M2, then if I take it to generate a new PM wave AC cos omega Ct plus Kp into M1 plus M2 of t, which is definitely not same as that of the additive signal which is generated here. So therefore, AC cos omega Ct plus Kp M1 of t plus A cos omega Ct plus Kp M2 of t is the signal. If I take the additive signal and then generate, so therefore I can't make it equal to xc1t plus xc2t. So therefore, it is not again satisfying the additivity property. No need of checking homogeneity. Homogeneity also can be verified for linear or non-linear. The given signal is also. So the FM wave and the PM wave are best examples of nonlinear methods of modulation. And even conventional AM, full carrier AM is also nonlinear. DSBSC is strictly linear method of modulation. So we'll move on to the next doubt asked by another student yesterday. What is the difference between the baseband signal and the magnitude of the baseband signal mod m of t? This is the baseband signal. Basically, every message bearing signal or information bearing signal which is used for the transmission of the information is the baseband. It is the base for transmission of the original information to be transmitted from a transmitter which is the generating station, which is far away located from the actual receiving station. So therefore, we want to use this to generate the transmission signal. So therefore, it is the original transmission signal that has not been modulated or has been demodulated or its original frequency. Most of the telecommunication protocols which requires the baseband signal to be converted or modulated to a high frequency or to occupy the higher frequencies to be transmitted over long distances. One of the reasons for modulation also we discussed in the first few classes of analog communication. So therefore, if this signal to be used as a transmission signal, it is to be capable of traveling over long distance. So therefore, the baseband signal or the low pass signal which is converted during the process of transmission, we call it as the process as being termed as modulation. So you can take, for example, Ethernet is an example of a particular signal transmission protocol that does not require any signal modulation since it transmits the data in baseband. If the signal is transmitted in baseband, its magnitude only being transmitted, that is modulus of m of t. Assume that if a baseband signal is of the form x equal to 3 plus 5y, its magnitude is, you know it, as it is a vector, 3 square plus 5 square and the square root will be the magnitude. Similarly, if the signal is of the form x of t is AC cos 2 pi fct or AC sin 2 pi fct, whose magnitude is the magnitude of the carrier. When you want to transmit the baseband signal as a modulated signal, the frequencies and all that will be converted by frequency translation, and the frequency of the modulating signal will occupy a new frequency band ready for transmission or ready to be traveled over long distances against the odds. Those odds are noise and distortion. Whereas here, if you transmit the baseband signal as it is, then the modulus or the magnitude part of it you are transmitting. So that is the difference between the baseband signal and the magnitude of the modulating signal. Hope I cleared the doubts. Now we will move on to the actual class of today's schedule. We scheduled today's class for transmitters and receivers. I would like to present today's class in this line. My presentation outline is, I will first cover the AM radio transmitters, the high level and low level transmitters we will discuss, AM and FM transmitters. Next I will discuss the FM transmitters. On completion of AM and FM transmitters, we will move on to the AM receivers, which is a very important concept. So the AM receivers as well the FM receivers also I am trying to cover today. I would attempt to cover, and on completion of the conceptual part, I will discuss few problems related to the recent GATE examinations. So now we will start our discussion with radio transmitters. So the learning outcomes for today's class are four. Students will be capable of demonstrating the construction and operation of AM and FM transmitters and construction of AM and FM receivers. Students will also be capable of understanding the concept of image frequency and how to reject the image frequency. And the fourth one is problems. It was wrongly being typed here. It's not comparison of FM and narrowband FM and wideband. We will try to do some problems as the fourth learning outcome. Now we will start with the AM radio transmitters. Normally, a communication system comprises of a transmitter, a channel, and a receiver. So therefore, we want to transmit a signal which is generated at the generating station. We also carry out the communication process, what we call it as modulation. So therefore, modulation is being carried out at transmitter. We want to make the signal for transmission. Modulation is carried out in the one of the functional blocks of the transmitter is modulation. After modulation, we need to make the signal to be sufficiently powered, and by using the right carrier frequency and having a good modulation process, and the kind of transmission should be capable of providing us a reasonably efficient way of communication. So on transmission, the channel will aid us. Channel will be any communication medium, let it be a wired channel or a wired channel. Whatever you have transmitted, this signal may be transmitted as a radio signal. Let us for example, the radio frequency bands are also ranging from the low frequency to high frequency, the very high frequency, ultra high frequency, super high frequency, as well extra high frequency. Likewise, 8-9 frequency bands are there. A particular application utilizes a particular band of frequencies for the transmission of this radio signal, which is generated at the transmission location. So therefore, earlier people used to use the basic concept of AM and FM without modulation. Also, we can transmit. We call such a transmission as baseband transmission. If you transmit like when the receiver is within vicinity, let us suppose you are in this room, your family member or your classmate or your friend is within vicinity communication, then you can clearly communicate by using the capacity of your vocal cords to communicate such an individual. But whereas in radio communication, one may be in India, the other may be in US, which are physically far separated. So in such cases, transmitters are very much essential. The electronic transmitters are very much essential. So this audio frequency or any information bearing signal need to be electrically converted, and it is to be transmitted through the channel. And at the same time, the capacity of the communication system will also be measured in terms of the reception quality. How best you will be capable of receiving this transmitted signal through the channel. Channel is a problematic part where the noise and interference will be induced or additively present. Why? Because for analog communication part of it, we will be considering only additive noises. We are not considering any other kind of noise. So therefore, noise and distortion may be added to this transmitted signal. And how best your receiver is capable of performing the separation of noise from the original signal, and then finally the information bearing signal may be extracted by a key process called as detection or demodulation. This is what is a communication process. So therefore, transmitter, if it carries more power, if it uses the right frequency of the carrier, and if it is capable of giving us a reasonable efficiency, then we can say that a particular transmitter can be an adaptable transmitter. So for that, we make use of an AM transmitter and FM transmitter. Basically, there are two types of transmitter. If you use amplitude modulation as the means of generating the transmitted signal, then we call those transmitters as AM transmitters. If you use FM as the means of generating the transmitted signal, frequency modulation or phase modulation, then we call them as FM transmitters or angle modulation transmitters. So broadly, we can classify AM radio transmitters into two categories, that is low-level modulation transmitters and high-level modulation transmitters. There is nothing much difference in between low-level modulated transmitters and high-level modulated transmitters. So they lies in if the generation of AM waves, that is the wave you are interested in transmitting, is being low-level modulation, initial stages of amplification. That is, in low-level modulation, the generation of the AM wave takes place in the initial stages of amplification. That is, At low power level, if you generate the signal, the kind of transmitter is called as low level transmitter. The generated AM wave is now without having a sufficient power, we cannot transmit the signal. The amplification by using a number of amplifier stages will be carried out later. The generated AM wave then amplified using number of amplifier stages. Such an AM transmitter is known as low level transmitter. That is, in low level modulation transmitters, the generation of AM wave takes place in the initial stages. First we will generate the AM wave, and then the low power generated AM wave is used at the further next stages. It is being amplified to the desired level and then transmitted. Those kind of transmitters are called as low level transmitters. You can see the block diagram of a low level transmitter, AM transmitter block diagram with low level. So a crystal oscillator, a class A RF buffer amplifier, class C power amplifier, class B RF linear power amplifier in this channel, and the audio input, what is your message you are interested in transmitting. Audio frequency pre-amplifier, it is boosted to the required amplification level, and then AF class B power amplifier, it is also power amplified by using a class B amplifier. Then it is modulated prior to giving it to the power amplifier stage. The modulation is being carried out. Modulator AF class B output amplifier, it is being generated and then given to the further stages for next power amplification, which is called as the low power modulator or low power AM transmitter. Then we will feed it to the matching network and to the transmitting antenna. So the radio transmitter of the next kind, AM radio transmitter of the next kind, is high level transmitter. Unlike the low level transmitter, in high level transmitter, modulation takes place in the final stages of amplification. So the fundamental difference between these two transmitters is, in the low level transmitter, modulation takes first and then amplification. In the high level transmitter, we first try to amplify the signal to the desired level, and then we will look into the process of modulation. So therefore, modulation takes place in the final stages of amplification. Therefore, the modulation circuitry has to handle high power. The kind of modulation is carried out after converting the signal to the power stage. So therefore, modulation is performed at later stages in the high level modulators, in the initial stages in the low level modulators. Whereas in the low level modulation, amplification is being carried out in the later stages. In the high level modulation, amplification is being first. So that's the fundamental difference between a high level modulator and a low level modulator. So this is how the block flow of a high level AM transmitter. Similar AF stabilized network, class A buffer amplifier, class C power amplifier, class C RF amplifier, the AF pre-amplifier and AF class B power amplifier, modulator AF class B output amplifier, and it is being amplified to the output stage, required output stage, output power stage, and then it is being radiated. So the AM radio transmitters, it can be seen from a stable RF source. It can be seen that stable RF source, buffer amplifier, and subsequent RF power amplifiers are common for both low level and high level transmitters. The RF source is provided by crystal oscillator with a carrier frequency or submultiples of the carrier frequency. Carrier frequency is supplied by the crystal oscillator. This is the modulating frequency. Both will be generating the modulated signal. Class A amplifier, whereas Class C power amplifiers, both will, buffer amplifiers are usually a Class C or Class A amplifier. Audio and power audio amplifiers are present. In fact, the only difference is the point at which the modulation takes place. If the modulation takes place initially, it is low power. If the modulation takes place later, it is a high power amplifier. So modulation takes place at lower levels, that is before final output amplifier, in the low level modulation transmitters. Okay. So the efficiency and bandwidth preservations are important factors since audio signal is having low power. Every audio signal is having low power. For high level modulation, other than efficiency of amplifier power, handling capacity, the distortion, the capability of handling the amplitude variations are also important parameters. We should also take into consideration Not only the low power or high power or modulation takes place at low level or high level. For high level modulation, other than efficiency of the amplifier, power handling capability, the distortion handling capability, or the capability of handling any variations in the amplitude can be handled by the transmitted signal or not should also be taken into consideration. The output of the final amplifier is passed through an impedance matching network. When impedance matching is being arranged in any signal transmission, maximum power will be delivered to the load. Ultimately, the kind of load we are interested in is the transmitting antenna is load for a transmitter. So therefore, at the ultimate delivery point, we have used a matching network to provide impedance matching. We all know that the impedance matching provides us with maximum power to be delivered or maximum power to be transmitted. That includes a tank circuit of the final amplifier. Why? Because all the modulated version of the signal is nothing but a kind of tuned signal. So therefore, it is provided with a kind of tank circuit at the final amplifier. So the tank circuit also should be provided with a good quality factor. Q is kept low enough to pass all the side frequencies without amplitude and frequency distortion. This point need to be considered. Q is kept low. Why? Because it has to pass all the side frequencies of the generated signal without any amplitude or frequency distortion. These points are to be taken care of before transmitting a signal. So in general, there is negative feedback also being utilized in AM transmitters. Why? Because you can see here a kind of negative feedback, a sampled signal through a linear modulator is again fed back to the system in order to sample the output signal. Why it is being provided? We all know that negative feedback gives better stability and better control over noise and distortion. Noise and distortion can easily be managed or minimized through negative feedback. Those are the fundamental reasons why a negative feedback is being employed in most of the AM transmitters. Generally, negative feedback is provided in AM. This negative feedback reduces the distortion in Class C modulator system. It also linearizes the output of the Class C modulator. The negative feedback circuitry is simple, not simple. Negative feedback circuitry will samples the RF signal sent to the antenna. You can see from this diagram what is the RF signal that is being fed to the antenna for radiation, that is being sampled. Okay, and then this sample signal is modulated by linear modulator to produce the feedback signal. Okay, that is being utilized by the linear modulator to produce the modulated version of the signal. Whatever the signal you want to generate, some part of the signal is sampled back and then generated as an AM wave. A tuned Class C power amplifier must be provided sufficient power gain to drive the fine. We all know that Class C power amplifier provides better gain at power stages. So therefore, tuned Class C amplifier. Almost all the amplifiers that are used in the transmitters are tuned amplifiers because a signal is a band of frequency carrying signal. So therefore, we must employ the tuned amplifier stages. At the final stage of amplification, we need the maximum capacity, power efficiency. So therefore, Class C amplifier provides that. The antenna systems for AM transmission must be located at some point remote from the studio of operation so that the interference may be minimized. That's about AM transmitters. Now we will move on to the FM transmitters. So we know that why we go for from AM to FM is fundamentally FM can perform better in the presence of noise and distortion. We know that. So why? Because AM requires less bandwidth and less power. FM requires more bandwidth and the amount of power that is being transmitted by every FM signal is always AC square by 2. So therefore, its capability for performing in the vicinity of noise and distortion is more. That is the reason why we move for FM transmitters than AM transmitters. FM signals have no amplitude variation. So we also know that FM is a constant amplitude signal. So therefore, FM transmitters can employ straight away the Class C amplification all throughout. Unlike AM, which make use of at some stages in the initially they make use of Class B power amplification. But here, right from the beginning, as there is no theoretical possibility of having any amplitude variations in the FM wave. So therefore, class C power amplifier can be utilized all throughout. Why I am using the word theoretically is when you try to look into the realistic or real-time signal for its capacity of variation. So if there is no variation in amplitude, why? What is the point in incorporating an amplitude limiter at the front end of every FM discriminators? So therefore, we all know that though the FM signal is a constant amplitude signal, so the variations in any amplitude part of the received FM wave need to be restricted. But theoretically, we say that FM signal is a constant amplitude signal. That is the reason why class C power amplifiers may be utilized at every stage of the transmitter building. So even after modulation also you can. So basically there are two types of transmitters, directly modulated and indirectly modulated. Directly modulated means a kind of FM wave is being generated and it is being frequency multiplied by using multiplier stages for further stages. That is direct method of modulation. Indirect method of modulation is nothing but first a kind of PM wave is generated and that PM wave is being utilized for generating an FM wave. We call it as an Armstrong kind of procedure. Yesterday's class also we have seen direct method and indirect method. Now we will discuss the directly modulated FM transmitters. Direct frequency modulation can be employed using any of the FM circuits. However, direct FM at final carrier frequency is not feasible because of the problem of maintaining high frequency stability of the carrier while at the same time obtaining adequate frequency deviation. Why? Because you need to get a good amount of frequency deviation to call the transmitted signal is a wideband signal. To solve this problem, indirectly modulating FM transmitters are being preferred. The frequency modulation is carried out at a low frequency and with a small frequency deviation, then passing the FM wave through a frequency multiplier. As we know, the desired carrier frequency and the desired frequency deviation can be achieved. With frequency multiplication, the instantaneous frequency is multiplied and to the desired deviation level. With frequency mixing, the deviation is not altered. One of the problems, okay, you can generate the wideband FM. One of the difficulties encountered in FM transmitters is that which depend upon direct method of frequency modulation, means direct FM transmitters. We know that the tuned circuits are being present in the transmitting stations. They will have the variable nature of inherently every tuned circuit will have a variable nature and the crystal control oscillators cannot be used and therefore the stability inherent in such crystal control units is not available. So therefore there is number of tuned circuits that we need. Why? Because the frequency is of variable nature, we cannot incorporate a crystal control oscillator which is capable of giving highly stable oscillated signals, which is a disadvantage with that. An alternative technique for generating a frequency modulated signal which permits the use of this highly stable crystal oscillator is an indirect method. So that is the reason why we move from direct method to indirect method. So in this technique, the phase angle is made vary because we know that in indirect way of generation of FM also, first we will generate a narrowband PM and then we will make it into an FM wave, a narrowband PM which is equal to AM, and then we want to make this into, by this technique, a phase modulated signal is generated and it can be passed off as an FM signal. A phase modulated signal is to be how converted into an FM signal, we all know. From PM to FM we make use of a differentiator, from FM to PM we make use of an integrator. So indirect modulation of FM scheme you can see here. Why? Because in the direct method of modulation, FM is first generated and then the frequency multiplication gives us the desired band of frequencies, which doesn't allow the use of a crystal oscillator. Why? Because the tuned circuit's frequency is variable nature. It cannot allows us for utilizing a crystal controlled oscillator. That is the reason why we move from direct method of FM generation to indirect method of FM generation, especially suitable for transmission. We are discussing transmission, not modulation. We are discussing transmission. So therefore a crystal control oscillator generates a carrier. The modulator amplifier generates the modulating signal. On integration, we will get a phase modulated signal to be converted into frequency modulated signal. That frequency modulated signal may be power amplified and then delivered through a transmitting antenna. This is how an indirect modulated FM transmission is being carried out. This is what we call it as an Armstrong method. The initial modulation takes place as an amplitude modulated DS-based signal so that the crystal controlled oscillator can be used if desired. The crystal controlled oscillator generates the subcarrier, which can be low, say in the order of 100 kHz. For example, one output from the oscillator is phase shifted by 90 degrees to produce the sine term, and which is then DS-based modulated in the balanced modulator Vm of t, V suffix m of t, or Am of t. This is combined with the direct output from the oscillator in the summing amplifier, and the result is then being phase modulated. That's how you generate a phase modulated signal. The modulating signal is passed through, this is the Armstrong procedure I am discussing. So the modulating signal is passed through an integrator to the modulator to get the frequency modulated signal. So the desired frequency modulated signal on generation, at this stage the equivalent frequency deviation which is derived is generally small, and the frequency deviation which is obtained is small. You can see here how the DS-based signal generated by the balanced modulator and with 90 degrees phase shifted and then summed up with the crystal oscillator generated carrier, and then utilizing a frequency multiplier, a phase modulated signal may be converted into a frequency modulated signal. In order to increase the deviation, we use a frequency multiplier and a down converter, and again another crystal control oscillator is being utilized to generate the desired high power FM wave to be transmitted, and the power stage amplification can be carried out by utilizing this FM signal generated may be fed to the class C power amplifier, and then a high power FM signal is ready for transmission that will be transmitted into space. So now the transmitters part of it is being completed. We have discussed the AM transmitters, the need for transmitters, the FM transmitters. Out of the FM and AM transmitters, two categories of transmitters we have discussed, the low power and high power, and the two categories of FM transmitters, that is the direct method and indirect method of generating FM transmission we have discussed. Now we will move on to the important concept of today's class, the AM radio receivers. So most number of questions are coming from radio receivers. So therefore we will try to discuss it in detail. So every AM radio receiver to complete the communication system, we have discussed so far about the transmitter, the channel. In detail, we have not discussed anything about the channel except for the channel induced distortion and noise. So to complete a communication system, this transmitted signal which radiates the signal, and the signal passes through the a wired channel or a free space like wireless channel are to be received. So how to receive the generated signal completes the communication system. So a complete communication system is nothing but transmission, reception, in between transmission and reception, the channel. We have not discussed anything about the characteristics of the channel. The reception process we now try to discuss. So AM radio receiver is a device which receives the desired AM signal, amplifies it followed by demodulation to get back the original modulating signal. So if you receive a signal straight away, we do not know what kind of signal it is. We don't know whether AM is used for transmission or FM is used for transmission. Out of AM, which AM is used for transmission? Let it be a full carrier AM transmitted signal, or DSBSC transmitted signal, or SSBSC transmitted signal, or a VSB transmitted signal. We do not know. So therefore, the radio receiver should understand what kind of signal we have received. If it is AM, our receiver should be of AM. If it is full carrier AM transmitted signal, we need to arrange a full carrier AM reception process. and thereby on receiving the signal power, we need to first pre-process, we need to check whether the figure of merit of the received signal is up to the mark or not, or otherwise we need to tune to the signal, and then ultimately before delivering it to the ultimate delivery device, which is an electronic loudspeaker in receivers. I am speaking about audio frequency signal reception. So when you are receiving an audio frequency signal, so therefore you need to carry out not only reception, tuning to the transmitted frequencies. On tuning to the transmitted frequencies, if AM is the transmitted signal, AM is the received signal. If FM is the transmitted signal, FM should be the received signal. So therefore you have to incorporate the corresponding demodulator circuits and corresponding tuning and selecting circuits. You need to select a signal. Let us suppose you are tuning to a radio station 1. When your receiver is tuning to, you are supposed to tune to radio station 1, let us suppose. When you are tuning to the signal, when a radio station 2 is being received, you are not supposed to receive that signal. You need to reject it. So therefore, how you are selecting it and how best you are providing the signal, what is of interest you are interested in receiving is being received. And then after receiving the signal, what is that we are supposed to do is, if it is AM, it is to be carried out by the best AM detector or AM demodulator. If it is FM, some or the other kind of FM discriminator or frequency demodulator circuit is to be arranged. So this is how we carry out reception. Not only tuning to the transmitted signal radiated by the transmitting antenna, at every receiver at the front end, we also incorporate a receiving antenna. That receiving antenna will be tuned to a band of frequencies. Out of the band of frequencies, we will try to separate the modulating signal. Why? Because the received signal will be again a band pass signal. Okay, so it is very, very low power signal. That's why at the front end of the receiver, we need amplifiers to be incorporated. That part of it also we will discuss. And then this received amplified signal is to be properly demodulated, and this demodulated signal is to be delivered. On delivery only, you will come to a judgment that whether the reception process is proper or not. It is being decided based on the quality of reception. We discuss in detail in a noise chapter about the capacity of the receivers. We are not discussing anything about the capacity of the radio receivers. How the radio reception process is being carried out, now we will discuss. So radio receivers are basically classified into two types. Depending on the application, we can classify the radio receivers into two types. They are depending on the radio, depending on the type of application is one category. Depending on the fundamental aspect or the principle that is used in the carrying out the reception process is another type. The first kind of receivers are AM receivers, FM used for AM reception, FM reception, or communication signal reception, or TV signal reception, or radar reception. They are depending on a particular application. The second category of receivers, depending on a particular principle of operation, and the second category kind of receivers are becoming so popular and commercial. So the commercial AM receivers we want to classify now. Commercial and popular AM radio receivers may be again categorized into two different categories. Way back to the 1940s and before that, people used to utilize a tuned radio frequency receiver as the first generation receiver, and later we use the second generation receiver, which is a super heterodyne receiver. So popular receivers are again two categories. There are two popular categories of receivers. One is a tuned radio frequency receiver, and the second one is super heterodyne receiver. What is the tuned radio frequency receiver? We now try to look into it. The tuned radio frequency receiver is a simple logic receiver. 2 or 3 RF amplifiers, all are tuning together. They were employed to select and amplify the incoming frequency. As I told you, every received signal will be a very weak signal in the order of microvolts or microamperes. If it is a voltage signal, microvolts. So therefore, that signal need to be amplified by using RF stands for radio frequency. So on tuning the radio frequency amplifiers, one or two stages of radio frequency amplifiers are incorporated at the front end of the receiver after the receiving antenna. So the incoming frequency and simultaneously to reject all others. So whatever the frequency to which you are interested, you need to receive it by the tuned circuit present in the RF amplifier and reject all other frequencies. If the signal was amplified to a suitable level, it was detected. Means ultimately you need to detect the signal, and the detected signal should be fed to the loudspeaker, which is a delivery device, after being passed through the appropriate audio amplified stages. So therefore, this is the reception process, and this process is simple to design, or the TRF receivers are very simple to design and align at broadcast frequencies, but they are facing certain difficulties, especially at higher frequencies. When you are receiving a high frequency signal, they become highly unstable. They will go to a tendency even to oscillate. So therefore, this problem is called as RF amplifier, which is present in the tuned radio frequency receivers, which are not capable of handling high frequency signals. They, instead of amplification, they the receiver tended to oscillate, which is a highly undesired thing. So therefore, the receiver become highly unstable. The stability of the receiver will be a question mark. So therefore, it is difficult to achieve sufficient selectivity also at this particular point of frequencies. Selectivity means selecting the desired frequency and rejecting the unwanted frequency. We will also look into the features or characteristics of a good radio receiver also. We will discuss in the latter part of our discussion. The bandwidth variation over a tuning range will also not same all throughout the tuning range of operation. The bandwidth that is being produced by the tuned radio frequency receivers is not good. So therefore, because of these three problems of instability, not good selectivity at high frequencies, and the bandwidth variations over the entire tuning range, makes the tuned radio frequency receiver, though it is simple and logical receiver, we cannot utilize it for most of the applications. So therefore, later people thought of designing another generation of receivers. So then that kind of a receiver we will discuss at length. The first RF amplifier, many number of cascaded RF amplifiers, similar tuned amplifiers that are connected at the front end of the receiver for this is the receiving antenna. The received signal is being received. Tuned reception process makes the signal to be amplified to the desired level. Next level of amplification, both are next detection, all are gang tuned, means the tuning is to a common control. Gang tuning is, it's a mechanical control of making all the functional blocks tuned to a particular frequency. Then on detection, the detected signal will be audio amplified and audio power amplified and delivered to the loudspeaker, which is load. Load is an electrical, which is like a transducer, which converts the electrically generated received signals, power amplified signals, into an audible sound which can be perceived by the human auditory system. So this is the process of reception in the tuned radio frequency receivers. These tuned radio frequency receivers are suffering from the problem of instability, not having the same bandwidth all throughout the tuning range, and unable to handle high frequencies, unable to select the desired frequency under the high frequency of operation, paved the way for the inventors. Thanks to the inventors who has invented the very good receiver, we call it as a super heterodyne receiver, which to heterodyne means, the English meaning of heterodyning means mixing. It mixes of a process called mixing. And these are the several different functional blocks about which we will discuss next after discussing the characteristic features. What are the features that are being required to accept a particular receiver as a receiver that can be adaptable? So therefore, the characteristic features of a receiver we will see. Before that, what are the functional blocks in a super heterodyne receiver which is being designed in order to overcome all the three difficulties faced by the tuned radio frequency receiver. At the front end, the receiving antenna, the TRF receiver, we have an RF amplifier. So after the RF amplifier, we have a mixer, followed by the mixer as a local oscillator. A locally generated carrier signal is being generated here. The local oscillator followed by the local mixer, another amplifier is being identified. We call it as intermediate frequency amplifier. The kind of signals that are generated by the mixer is the local oscillator will be always made to operate at a higher frequency when compared to the incoming signal frequency by an amount which is equal to the intermediate frequency. So therefore, the difference frequency is being generated as an intermediate frequency. So therefore, in general, the local oscillator will be generally operated at a higher frequency when compared to the incoming signal frequency. So therefore, the new frequency that is generated by the mixer is being fed to the IF we call it as the intermediate frequency signal that is fed to the IF amplifier. Next to the IF amplifier, we carry out the actual detection process. This IF amplifier and the mixer part of it we have not observed in the tuned radio frequency receiver. So next we carry out the AM detection process. If it is an AM wave, that is, we are discussing about AM super heterodyne receiver. So therefore, an AM detector is straight away being utilized. If it is an FM receiver, prior to detection, you have to incorporate a limiter. That is the only difference between an FM receiver and an AM receiver. That part of it we will see in the latter part of today's discussion. The next is the audio frequency power amplifier. Similar to the previous TRF receiver, we use a loudspeaker, which is again a transducer which converts the electrically generated AF signal to be delivered through the loudspeaker. This is how the arrangement is being present in a super heterodyne receiver and its functional blocks. So, before discussing in detail about the super heterodyne reception process, what are the required characteristics of a good radio receiver? We will now see. Sensitivity, selectivity, fidelity, and adjacent channel selection, we call it as double spotting. Image frequency and image frequency rejection are the characteristic features of a good radio receiver. What is what we will now see. So sensitivity is defined as the minimum RF signal level that can be detected at the input of the receiver and produced a usable demodulated information signal with a minimum acceptable signal to noise ratio. So again, we have an acceptable level of signal to noise ratio. So what is the minimum RF signal level that can be detected at the input of the receiver, and it produces a usable demodulated information. If you cannot produce a usable demodulated signal, then it is of no use. Receiving such a signal is of no use. So therefore, the sensitivity of the radio receiver is minimum RF signal level which produces the desired acceptable signal to noise ratio. Then if the desired minimum acceptable signal to noise ratio is received, then it can be considered as a signal to be detected. Once after detection, what is that we will do? We will pass it to the AF amplifier and AF power amplifier, and then we will deliver it to the loudspeaker. This sensitivity for commercial AM broadcast receivers is an order of 50 microvolts. The sensitivity of the AM broadcast receivers is in the order of, once again, sensitivity is the minimum RF signal level that can be detected at the input of the receiver, which produces the usable demodulated information with a minimum of acceptable signal to noise ratio. So the sensitivity curve you can see here. On x-axis the input signal and on y-axis the received input signal level. So as you can move from the frequency band, this is what is the signal input signal frequency. You have to, this is what is the acceptable sensitivity, and after that you can say that if this is the kind of frequencies that are being generated, the received input level is not satisfying the requirement, the sensitivity is set to be good here, lowest here. Okay, received signal levels should be at the minimum acceptable signal to noise ratio. Sensitive means it is to be responding to the what is the minimum weakest signal that the receiver is capable of producing the output. That is what the sensitive. It should be as low as 50 microwatts for a broadcast, as this is the smallest point where the receiver is capable of generating the received signal which can be detectable. So therefore, its sensitivity is highest, whereas here the sensitivity is lowest. The next characteristic feature of the radio receiver is selectivity, means how good the wanted frequencies are being separated from the unwanted one. So therefore, used to measure the ability of the radio receiver to accept the given band of frequencies and reject all other frequencies. So therefore, to which band of frequencies you have designed your receiver, to that band of frequencies your receiver should be tuned to. So if it is tuned to the desired frequency band of interest and rejecting all other frequencies, then we can say that my receiver is a highly selective receiver. So now you can see the selectivity graph. It's like the resonant circuits frequency response, where frequency on this, attenuation on this, which is on y-axis, and frequency on the x-axis, where the receiver tuned to a particular frequency, which we can call it as a resonant frequency, attenuates all other, increase away from the tuned frequency, which will attenuate all other frequencies. It is something like a selectivity graph of a resonant circuit. So therefore, highly selective tuned circuits you need to incorporate at the front end of the receiver. The front end unit of the receiver is nothing but RF amplifier. So the RF amplifier will play a very vital role in selecting the signal to which you are tuning the entire receiver. This is an important point one should keep in mind. So the next kind of characteristic feature that we should take care of is the fidelity. Fidelity is the ability of the receiver to reproduce all the modulating frequencies of the original information, whether the received frequencies are being fully reproduced or not. What is that? You are receiving the modulating frequencies you are receiving in a modulated way by a transmitter. So therefore, out of the modulated signal, you need to recover the modulating frequency which carries the original information bearing message. So that is to be properly received, and it is to be reproduced for all modulating frequencies. For the entire range of frequency of the modulating signal, the original information is to be delivered to the loudspeaker. That is what is being termed as fidelity. Fidelity is being graphically represented with the frequency on x-axis and the receiver output on the y-axis. So therefore, you can have the minimum attenuation that is being provided to the entire tuning range of frequencies ranging from 50 Hz to 10 kHz. For this particular figure, we have used this range of frequencies, which will be the audio frequency range. So it is the ability to reproduce, ability of the receiver to reproduce all the modulating frequencies in the original information. The next characteristic feature of the radio receiver is adjacent channel selection or the double spotting. This is a well-known phenomenon which manifests itself by picking up the same shortwave station at two nearby points on the receiver dial. When on the receiver dial, when you are receiving the same station at two different stations, it causes an annoying sequence to the listener. If it is a radio which is being tuned at two different points, it is not being to the satisfaction of the receiver, which causes poor front-end selectivity. If the front-end selectivity circuit, which is nothing but the RF amplifier, doesn't tune to the station to which you are interested in tuning, if you are tuning to two nearby stations on the receiver dial, one after the other, picking up the same shortwave station at two nearby points, then it doesn't give you the good reception, which results in double spot. This problem is called as double spotting. It is the reason for this problem is the poor front-end selectivity of the receiver. The front end of the receiver does not select different adjacent signals very well, but the IF stage eliminates almost all of them. So therefore, finally, we have just so far discussed about RF amplifier as the ultimate functional block which take care of the selectivity, but also the IF amplifier. But the IF stage eliminates almost all the nearby frequencies that are being tuned. So therefore, it is ultimately being decided by the IF amplifier. So double spotting may be used to calculate the intermediate frequency of an unknown receiver. Whenever an unknown receiver at the nearby station is being tuned, the same double spotting problem we can explore it for our advantage of calculating what is the station to which we are tuning to, what is the intermediate frequency of the unknown receiver, since the spurious point on the receiver dial to which an unknown frequency you are dialing. So therefore it is being utilized to the military people utilize this property of double spotting to identify the enemy target and its receiver's intermediate frequency. 2Fi below the correct frequency, Fs below 2Fi, we call it as the spurious frequency. It is being renamed in the later part of the discussion, which causes a lot of problems to the receiver. We call it as image frequency. That is another problem. Here itself we can discuss. The next characteristics of a radio receiver is image frequency and its rejection. What is image frequency? A particular spurious frequency or a particular frequency which is unknown, which manages to reach the output of the mixer. Actually, the output of the mixer should be, as you can see from the heterodyne receivers working. Briefly, we discussed the heterodyne receivers working. A particular frequency, which is the signal frequency, and the difference of the signal frequency to the log oscillator frequency. Mostly the log oscillator is made to operate just above the signal frequency by IF amount. For AM super heterodyne receivers, the IF value will be in the order of 455 kHz. Mostly the log oscillator, it is not operated always with a fixed frequency. It is a frequency which is IF times incremented by the signal phase. So the difference frequency is always whatever may be the signal frequency that is received, the difference frequency, that is F0 minus Fs, should be always equal to the intermediate frequency. So the selection, let us suppose a double spotting has happened due to the poor front-end selectivity of the RF amplifier. Because of the double spotting, another spurious signal manages to reach the output of the mixer and enters into the IF amplifier. Once if any signal enters into the IF amplifier, it is being amplified and then detected, and the receiver will assume that it is the signal which is supposed to be demodulated. It detects it and then delivers in the loudspeaker, which is a big problem when the signal to which you are interested in tuning is not tuned and it is delivered in the receiver. Such a problem is called as an image frequency problem. A spurious frequency which manages to reach the output of the mixer and manages to pass through the IF amplifier and detector and then delivered in the loudspeaker is known as an image frequency. Such frequencies are to be identified and then rejected. The image frequency rejection ratio can also be considered as the characteristic feature of a radio receiver that is supposed to be very good. The image frequency may be calculated like this. The intermediate frequency, as we discussed, the log oscillator frequency minus the incoming signal frequency. FLO is nothing but F0 minus FRF is the radio frequency, that is the signal to which your receiver is tuned to. So therefore, the difference frequency, we want to take it as the intermediate frequency generated by the mixer. That is being given to the IF amplifier, that is supposed to be amplified to the desired level and detected, then it is to be amplified prior to delivery. That is the actual process of super heterodyne reception. Image frequency is a frequency which is additively present with the log oscillator frequency by the same amount of IF, and thereby if you see FLO, which is nothing but, you can say that the log oscillator frequency is intermediate frequency plus the received frequency. So FLO is equal to FIF plus FRF. If you substitute for FLO here, FRF plus FIF is being present in addition to the image frequency, intermediate frequency that is supposed to be generated by the mixer, and log oscillator combination. Mixer log oscillator combination by receiving the signal actually generates the F. Now, the frequency of the signal, if FLO plus FIF is the signal to which the mixer is tuned and then delivered, then it is called as an image frequency, which will be the RF signal frequency plus 2 times the intermediate frequency. Such a frequency causes lot of disturbance or distortion, and the performance of the radio receiver will be entirely suffer with such problems. Such a frequency need to be restricted, not to pass through the mixer and IF amplifier stage. How good the receiver is able to identify the image frequency and reject the image frequency is the ability of the good radio receiver. So therefore, image frequency rejection ratio of an image frequency signal by a single tuned circuit may be defined as the ratio of the gain by designing a single frequency tuned circuit, a signal frequency to gain at the image frequency. By designing a tuned circuit at the mixer, we can carry out the image frequency rejection process. Now we see the calculation of image frequency once. Let us suppose FL is the log oscillator frequency and FS is the image frequency. Then the difference between the log oscillator and the signal frequency or RF signal frequency. So we call this process, so why I am discussing this is to do problems. For down conversion, we call the general process as down conversion. In general, the log oscillator frequency will be higher than the incoming signal frequency by IF amount. This is a general standard. At times, up conversion will also be taken place, that is, log oscillator plus the signal frequency will also be considered as IF, where FL is the log oscillator frequency and FS is the incoming signal frequency. We use IF as a standard from hereafter for doing problems, intermediate frequency. So the image frequency is nothing but FSI, as we know that, which is the log oscillator frequency plus the intermediate frequency. If the log oscillator frequency FL plus intermediate frequency IF under down conversion, if you say FL is equal to FS plus IF, if FS plus IF is substituted here, FS plus IF plus again IF is the image frequency. So FS plus 2IF. Here we have defined it as FRF plus FIF. So this is what is the kind of image frequency for a down conversion. FS is the image signal, incoming signal, IF is the intermediate frequency. If the frequency of the receiver signal is greater than the log oscillator frequency, if this is what is the case, if the frequency of the receiver signal is greater than, why? Because we can definitely say that log oscillator frequency is IF minus FS. So in this case, the image frequency is to be differently being calculated. Fs is equal to Fs minus 2IF. We need to remember this important point in mind. If the frequency of the receiver signal is greater than the log oscillator frequency, we need to use this formulation for calculating image frequency. Otherwise, if this point is not specified in the problem, we can take this as the formulation for computing the image frequency, which is Fs plus 2IF. How to calculate image frequency rejection ratio? The image frequency rejection ratio is by selecting a tuned amplifier for such a purpose and then rejecting this frequency, as I told you, is a solution. The image frequency rejection ratio is the gain of the such a tuned amplifier, the gain offered by the tuned amplifier to the Fs, that is the incoming signal, divided by the gain offered by the tuned amplifier to the image frequency Fsi. So the gain offered by the tuned circuit, which is being developed in the super heterodyne receiver for rejecting the image frequency, and the gain offered for the incoming signal frequency Fs, which is being tuned by the RF amplifier, divided by how much amount of gain that is being offered by the same tuned circuit to the image frequency. That ratio you need to calculate. We call it as image rejection ratio alpha, which is equal to gain for the signal and gain for the image frequency. If tuned amplifiers are connected in cascade, then effective image frequency rejection, if number of such tuned amplifiers that are connected for such a purpose of image frequency rejection, then the gains of all such amplifiers are to be multiplied because they are cascaded. When similar amplifiers are cascaded, their gains can be producted in order to compute the effective gain of the cascaded configuration. Alpha 1, alpha 2, alpha 3. If alpha 1 is gain of the first tuned circuit which is connected for the rejection of image frequency up to alpha n, we need to consider. If GS and GFSI are not known, then the image frequency rejection ratio, if the gains are not being given in the problem, the image frequency rejection ratio can be calculated by this formulation. Alpha is equal to square root of rho square q square plus 1, q1 square plus 1 into rho square root q2 square, q1, q2, q3 are nothing but the quality factor of each and every tuned circuit that are being connected in cascade. If a single circuit is being there, we can calculate the Q factor like this. Not Q factor, the rho which is constant can be calculated to calculate the image frequency rejection ratio, which is alpha. So a constant rho is being computed in between in order to substitute for the calculation of image frequency rejection. Fsi by Fs minus Fs by F. Hereafter, we want to call the image frequency as Fsi. The incoming signal frequency to which the receiver is tuned to is Fs minus Fs by Fsi. And the bandwidth is the resonant frequency divided by the Q factor of the resonant circuit that is used for the purpose of image frequency rejection, where Fr is the resonant frequency, which may be computed as 1 by 2 pi root LC, and the Q factor can be calculated as the quality of the resonant circuit used for the purpose may be calculated as 1 by 2 pi root L by C. So here itself, before doing a problem, one or two problems we will do in order to break the monotonous theory delivery, and then a few problems we will, for the first 1 hour we have not discussed any problems except for discussion of the doubts raised by a few students. We'll again go back and then see the working in detail of a super heterodyne receiver. This part of it I skipped. Why? Because the characteristics of a radio receiver, super heterodyne receiver, is to be known first. Then the functional blocks, one after the other, please do recollect it. The RF amplifier connected to the receiving antenna, followed by the RF amplifier, the new frequency generating circuit, which we call it as the mixer. Because of this mixer only, we call it as a super heterodyne receiver. So the mixer takes up the locally generated signal, which is always higher than the received RF signal by the RF amplifier, generates a difference signal which is called as the intermediate frequency signal connected to the AF amplifier. So therefore entirely whatever the frequency to which you are tuning to is not being given to the next stages. We have converted it to a new frequency. That's why this conversion may be called as mixing and generating a new frequency called as intermediate frequency. So that intermediate frequency, for every communication receiver, if you are generating frequencies known to all, then spurious receivers can receive your signal and they can make use of your communication system, communication resource. So therefore, the new frequency conversion took place here. That is detected, and then that will be amplified or power amplified, audio frequency amplifier or audio frequency power amplifier. and then the electrical signal may be delivered through the transducer. What we incorporate here for the delivery of the audio frequency signal is the speaker. The incoming signal voltage is combined with a signal generated in the receiver. This local oscillator voltage is normally converted into a lower fixed frequency. We call it as IF. The signal at this intermediate point contains the same modulation as the original carrier. No change in modulation, and there is no amplified signal and a detected signal to produce the original information. The superheterodyne, we call it a superhet, has the same essential component as the TRF receiver. In addition, we have a mixer and local oscillator and IFM. These three functional blocks are missing in TRF receiver. A constant frequency difference is always being maintained between the local oscillator and the RF amplifier, normally through capacitive tuning. In this, all the capacitors are, I forget to mention this point, all the capacitors in the tuned circuit are being tuned. You can observe a dotted line here. This is what is used for AGC control, and at the same time, the capacitors in this circuit, in this circuit, in this circuit, and this circuit, in the tuned circuit, are being connected to a common mechanical control. We call it as gang tuning. Why? Because we want to operate them in a uniformity. We call it as unison by one control knob. We call such a control as gang tuning. In the next diagram, in the next superheterodyne receiver diagram, I will show you. If IF amplifier generally use 2 or 3 transformers, each consisting of a pair of mutually coupled tuned circuits, with this large number of double tuned circuits operating at a constant specifically chosen frequency, the IF amplifier provides most of the gain and bandwidth required to the receiver. Most of the gain and bandwidth that is required to the receiver is being offered by the IF amplifier. The characteristics of the IF amplifier are independent of the frequency to which the receiver is tuned. Why? Because the receiver is tuned to a frequency Fs. IF amplifier is taking the difference frequency of the local oscillator and RF amplifier generated signal. So the selectivity and sensitivity of the superheterodyne is usually fairly uniform throughout the tuning range and not subjected to variation that affects the TRF receiver, whereas in TRF receiver such a facility is not there. So the RF circuits are used mainly to select the wanted frequency and reject the interference such as image frequency, and especially at high frequencies to reduce the noise figure of the receiver. This is also a facility that is there in superheterodyne receiver. Image frequency rejection is not possible in TRF receiver. If IF signal output is amplified, which composes of the modulated RF transmitted signal, and combining this with the RF, that is the received radio frequency from the local oscillator, then generating the IF is the actual principle. The detector eliminates one of the sidebands still present and separate the RF from the audio component of the other sideband. If we are specifically know the kind of received signal, then we can mention this point. Otherwise, we do not know what kind of a signal is to be received and what band of frequencies is to be selected and what is the band of frequency that is to be rejected. The RF is filtered to ground, that is the high frequency component is filtered to ground. The audio is supplied to the audio stage because it is the function of the detector for amplification, and then so to the speakers. The basic advantage with this is no variation in bandwidth. The bandwidth remains constant in the entire tuning range of operation of the receiver. High sensitivity and high selectivity is offered by superheterodyne receiver. High adjacent channel rejection also will be offered by the receiver. Without knowing all this, how can I explain about the selectivity, sensitivity, adjacent channel rejection, what we call it as the double spotting problem, and image frequency rejection and all that. That's why I thought of discussing the characteristic features first and then this next. So again, we need to identify the image frequency, generally termed as Fs plus 2 times IF. At times, if the received signal is greater than the local oscillator frequency only, we have to consider this formulation for the computation of the image frequency. Now we will move, this part of it is for the computation of image frequency rejection ratio. A superheterodyne, note down the problem. A superheterodyne, it's a simple problem, not so complex. A superheterodyne receiver, radio receiver with an intermediate frequency of 455 kHz is tuned to a station operating at 1200 kHz. The associated image frequency is how many kilohertz is this question. In most of the radio receivers, the localized frequency is higher than the incoming frequency. We assume that not assume, it's a general standard that the localized frequency is quite higher when compared to the incoming signal frequency. So therefore, F naught is equal to Fs plus If. If is given to be 455 kilohertz. Fs plus Fi. Okay. Fi is Fs is the signal frequency, and Fi or Fsi is the image frequency. If Fs plus Fi is the localized frequency, Fi should not be used in order to represent the image frequency. So Fsi may be the image frequency. Note down Fsi as the image frequency. So if we know that image frequency is nothing but Fs plus 2 times If. So therefore Fs plus 2 times If we can calculate. So F naught is a superheterodyne receiver with an intermediate frequency. If is being given, and Fs is also being given as 1200 Hz. So the signal frequency is 1200 and the intermediate frequency is 455. From the definition of the image frequency, signal frequency plus 2 times the intermediate frequency. That's it. Signal frequency plus 2 times the intermediate frequency is signal frequency plus 2 times the intermediate frequency. Signal frequency is 1200. Intermediate frequency is 455, so 2110 is the image frequency. Next problem. So the image channel selectivity of superheterodyne, image frequency channel selectivity, or image signal channel selectivity, or image channel selectivity of the superheterodyne receiver depends upon A, IF amplifier only, RF and IF amplifier only, pre-selector, RF and IF amplifiers, pre-selector and RF. This question was asked in 98 gate examination. We all know that the image rejection depends on the front-end selectivity of the radio receiver. Front-end selectivity first carried by the RF amplifier, final selectivity is being offered by the IF amplifier and must be achieved before the IF stage. It is to be achieved before the IF stage. If any spurious signal manages to reach the IF amplifier, then the signal will result in image frequency, and that is a big causes an annoying sequence to the ultimate receiver. So therefore it is to be stopped. So image channel selectivity depends upon the pre-selector, the front-end selector, if at all the tuned circuit comprises of any pre-selector and the RF amplifier. If it enters the IF stage, it becomes impossible to remove. So therefore it is to be restricted prior to the IF amplifier. Prior to the IF amplifier, what are being present? Prior to the IF amplifier, the selection is totally being carried by these tuned circuits comprised of RF amplifier, RF mixer and the local oscillator. Ultimately, if any pre-selector stage is being present, that need to tune to the desired frequency by rejecting all unwanted frequencies. So therefore, IF amplifier doesn't play the key role in rejection. If it is present, it will take any signal that is being fed to the IF amplifier, though it is being designed to be tuned to a particular frequency. There is no guarantee that it will also be tuned to the image frequency. If image frequency manages to reach the IF amplifier input, so therefore it is the out of the given question, it is the IF stage. It is the pre-amplifier and RF amplifier stage. They are the functional blocks which are responsible for the image channel selectivity. So therefore, out of A, B, C, pre-selector and RF amplifier, the AF amplifier is not the case. So therefore, pre-selector and RF amplifier need to do that function. So now we will see various functional blocks in detail and how they will be working. It is already 4:30. In another half an hour we need to conclude. So therefore quickly I will pass through the different functional blocks and then we will move on to problems. RF section and characteristics, frequency changing and tracking, intermediate frequencies and IF amplifiers, detection and automatic gain control. RF selection and characteristics. RF selection comprise of an input tuned circuit, an amplifier and output tuned circuit. It will be tuned to the frequency to which the receiving antenna is being tuned, and then giving it to the RF amplifier, and then generating this as an amplified tuned output fed to the mixer is the RF front end amplifier. The reasons for use and functions of the RF amplifier quickly go through: greater gain and better sensitivity, improved image frequency rejection, improved SNR, improved rejection of adjacent unwanted signals and better selectivity, better coupling of the receiver to the antenna, prevention of the spurious frequencies from entering the mixer and heterodyning there to produce an intermediate frequency equal to the IF from the desired signal, prevention of the re-radiation of the local oscillator. At times, there is a possibility that if the local oscillator re-radiation comes into picture, then it will become a big problem. That is the reason why we use an RF amplifier. Prevention of the re-radiation of the local oscillator through the antenna of the receiver are also the functions of and the usefulness with the RF amplifier. A typical circuit of an RF amplifier for mid-band frequencies and VHF we can observe. A single tune transformer coupled amplifier is most commonly employed for RF amplifier. Which RF amplifier is used for as RF amplifier? Single tube transformer coupled amplifier is most commonly preferred, which you can see. So next, frequency changing and then tracking. Mixer is a non-linear device having two sets of input terminals and one set of output terminals. Why? Because it takes a signal from the RF amplifier, another input from the local oscillator. The output that it gives is IF, that is single. The signal from the antenna or from the preceding RF amplifier is fed to one set of input terminals and the output of the local oscillator is fed to other set. Such a nonlinear circuit will have several frequencies present at its input, at its output, including the difference between the two input frequencies, and this was called the lower sideband of the frequency. The most common type of mixers are bipolar transistor FET based, dual gate MOSFET based mixers, IC mixers also being used. Here we will discuss self-excited mixers and separately excited mixer. A separately excited mixer you can see here. It's a device which acts as a mixer while other supplies the necessary oscillations. Separately a mixer circuit you can see. In the circuit in detail we can also study. The self-excited mixer circuit you can see here. There are two kind of mixer circuits, so basically self-excited and separately excited mixer, which generates the IF, which comes from the intermediate source, and whose output is tuned to the IF. Both these amplifiers are C amplifiers. And in here you can see, as I told you earlier, in the super heterodyne, these are all the tuned circuits present in the RF amplifier and local oscillator are being mechanically connected to a common control. We call it as gang tuning. So super heterodyne tracking, you can see now, to understand the process flow, to receive a tuned frequency, IF requires 550 as IF. The local oscillator will generate a frequency 1005. The mixer will produce a usable output to 455 kHz. The receiver is tuned, let's suppose, to 555. The local oscillator should generate 1005. Why? Because 550 plus 455 it is to generate. The mixer output is fed to the IF amplifier. The converted signal is rectified and filtered to eliminate the unusable portions. The amplifier and then it is amplified for listening. To understand the super heterodyning process, by taking a typical example, this is what is the flow. The received signal, let us suppose, is of 550 kHz. The local oscillator should generate 1005 kHz. The mixer will produce, the difference 455 is IF. So therefore, mixer need to generate this. So these two combined, they should be generated by the local oscillator. The mixer output, which is 455 kHz, is fed to IF. The converter signal is then rectified and then filtered. Rectified filtered operation is being performed by the detector circuit to eliminate the unusable portions, and next it is amplified for the listeners to be satisfactory. So tracking, super-data and receiver has a number of tunable circuits which must all be tuned correctly if any given station is to be received. The gang tuning is employed to do this work, which mechanically couples all tuned circuits so that only one tuning control in the receiver dial is being present or required. Usually there are three tuned circuits: antenna, RF and mixer tuned circuits, and law class tuned circuit. All these circuits must be tuned to get proper RF output input and to get IF frequency at the output of the mixer as a standard one. The process of tuning the circuits to get the desired output to the process what is being followed to get the desired output is known as tracking. Often we come across tracking errors. Any error that exists in the frequency difference because of the incorrect frequency being fed to the IF amplifier, such errors are called tracking errors and they are supposed to be avoided. To avoid tracking errors, standard capacitors are not used. Gang capacitors with identical sections are used. Different values of inductance and special extra capacitors called trimmers and padders we can use for adjusting the capacitance of the oscillators to proper range. We can quickly go through the padder tracking, trimmer tracking and 3-point tracking, and this is what is a padder tracking, and this is the kind of tracking error, positive error we have produced. This is a trimmer tracking, a negative error is being produced. You can see the trimmer and padder circuits separately, and if these two are combined together, the negative and positive errors, that is tracking error because of the padding, tracking error because of the trimming, can be minimized. Whatever the maximum and then minimum, the negative and positive both will be combined in order to have a 3-point tracking at one by the trimmer, tracking at the other by the padder, and a 3-point tracker will make a midpoint tracking where the tracking error may be minimized. So therefore, a 3-point tracking is generally employed in order to avoid the tracking errors. Then IF. The following are the three major factors influencing the choice of IF. If IF is too high, poor selectivity and poor adjacent channel selection results in useless sharp cutoff filter with the results of unless sharp cutoff filters are used in the IF stage. One additional thing we all need to remember is sharp cutoff filters we need at the IF amplifier because it is to be tuned to a fixed frequency of, for example, generated by a mixer for AM superheater and receivers, which we can say that 455. Unless you use sharp cutoff filters, we cannot physically by realizing sharp cutoff filters is again a question mark. A high value of IF we should not be chosen, okay, which increases the tracking difficulties also. If IF is at the same time lowered, we will face the same old problem of image frequency rejection, and rejection becomes poorer. We should not go for the too high value or too low value. A very low IF make the selectivity to be too sharp, cutting off the side bands. This problem arises because of the Q must be low enough when IF is low, and therefore the gain per stage is dropped or lowered. If IF is low, the frequency stability of the local oscillator must be made corresponding to the higher values, because any frequency drift is now a large properties of the low IF than a high IF. The IF must not fall within the tuning range of the receiver, and at the same time, or else instability will occur. So frequencies that are generally used for general AM broadcast, we can see here 438 to 465 kHz is used as IF in AM receivers with a standard IF value of 455 kHz. By far the most popular frequency is that. For SSB, these are the frequencies. For FM, these are the frequencies. For TV, these are the frequencies. For microwave and radar, these are the frequency ranges that are used especially for IF stage. One can note it down. the IF amplifier functional diagram. After noting down, we will quickly go through the problems. Another 25 minutes is left over. We can do good problems now. So this is the circuit diagram of an IF amplifier. So another important point one should remember is the detection and automatic gain control. Detection is being carried out for all AM receivers. The best AM receiver, the AM reception process is being carried out by making use of an envelope detector at the detector stage of the AM receiver. So therefore, the AM receiver provides the desired detection, and automatically a kind of another facility, AGC, is to be provided. The gain control is nothing but AGC is nothing but automatic gain control. The simple diode detector has the disadvantage that V0 in addition to Vn proportional to the modulating voltage also has a DC component, which represents the average envelope amplitude, which is the carrier strength, and small RF ripple. The unwanted component may be removed. It is the problem with the envelope detector. A small ripple may be present in all envelope detector output, which can be removed by filtering. In practical detectors, leaving only the intelligence of some second harmonic of the modulating signal, then it will become a problem. So therefore, practical diode detector, we can employ a practical diode detector like this. So automatic gain control, or AGC, is a simple system by means of which the overall gain of the radio receiver is varied automatically with the changing strength of the receiver signal to keep always the output substantially at a constant value. A DC bias voltage that is derived from the detector and connected with the practical diode detector circuit, and it is applied to the selected number of RF, IF and mixer by extracting a DC bias voltage and giving it back to the RF, IF and mixer is known as automatic gain control. This is being required in order to make the response of the receiver substantially at a constant level. For correct AGC operation, the relation between applied bias and the transconductance need not be strictly linear. As long as the transconductance drops significantly with increased bias, the overall result of the receiver output can be seen here. This is a delayed AGC circuit, and a delayed AGC uses two separate diodes. You can observe here. Okay, and the detector and the AGC, one at the detector and one at the AGC, they can be connected either to separate transformer winding as shown in the circuit, or both may be connected to the secondary without too much of interference. A positive bias is applied to the cathode of AGC diode to prevent conduction until a predetermined signal level is been reached. So these are simple AGC, and without any AGC, the response of incoming signal strength versus the received output. Two more kind of AGCs may be incorporated. Ideally, we need a standard gain to be always produced by the overall receiver. This is delayed AGC curve. This is simple AGC where there is no AGC. This is amplified AGC. Amplified AGC, delayed AGC. You can see. Now we will move to an FM receiver. The only difference between an FM receiver, the received signal should be an FM transmitted signal. All the other functional blocks are same except for the change in frequency of IF. The different IF is being used by FM receiver. And prior to detection, we use all FM demodulators here, and de-emphasis is to be carried out. This is sometimes optional, but amplitude limiter you need to incorporate, because a frequency modulator signal need to be a constant amplitude signal. If not, you should make it as a constant amplitude signal by incorporating at the front end of the FM detection process an amplitude limiter to make the received FM signal as a constant envelope signal. Thereby the detection and the reception process will be same. Whatever is the pre-emphasis means boosting the signal strength at the higher audio frequencies. Similar amount of compensation has to be carried out We call that compensation as a de-emphasis. Except for these two functional blocks and the type of detection and the amount of IF that is generated here, the entire functioning of the AM and FM receivers are same. The only change is a different IF, an amplitude limiter is must, a different process of detection by using all FM demodulators, and de-emphasis is to be employed at the FM receivers. Now we will move on to the problems. Again, we will recollect this important concept, like to calculate the intermediate frequency, that is the difference between the RF signal frequency that is received and the local oscillator signal frequency. The difference between the local oscillator frequency and the signal that is received by the receiver. For down conversion, all throughout down conversion is being going on. So the image frequency, which is the sum of the intermediate frequency and the received frequency. So therefore, the Fs value plus 2IF, we will get it as image frequency. For up conversion, it is something different. And if the problem, if the received signal is greater than the local oscillator frequency, then to calculate the image frequency, we have to use this. The image frequency rejection process is to be carried out with alpha square root of rho square q square plus 1, where rho is defined as Fsi by Fs minus Fs by Fsi. If it is not given that the received signal is greater than the local oscillator frequency. If it is not specifically mentioned, we can go out solving the problem with this procedure of calculation of bandwidth and Q factor. Now note down the first problem. A receiver is tuned to 600 kHz and intermediate frequency of 450 kHz. Find FL and Fs. Simple problem. FL is nothing but the local oscillator frequency, which is always IF times more when compared to the incoming signal frequency. So therefore, we need to compute FL minus Fs as IF for down conversion, FL plus Fs as IF for up conversion, and FL is equal to IF plus Fs. So the image frequency is Fs plus 2IF. We know we can calculate Fs plus 2 times the intermediate frequency 450 that is being given. Always the local oscillator frequency should be greater than the incoming signal frequency. Specific condition is not given, so therefore we have not used the up conversion. We have carried out the problem with the down conversion only. Next problem, a receiver is tuned to 500 kHz. Local oscillator frequency is given as 1050 kHz. Find the intermediate frequency and image frequency rejection ratio. Image frequency, comma, image frequency rejection ratio if the quality factor Q given to be 50. So here the local oscillator frequency is 1050. The incoming signal frequency, the receiver is tuned, so therefore it is what is the signal frequency 500 kHz. So we can calculate the intermediate frequency as the difference of these two, which is higher. We have to see local oscillator frequency is at higher level, so therefore it is down conversion. The FL minus Fs is the intermediate frequency, which is obtained to be 550. We know that the image frequency is Fs plus 2 IF. So Fs is 500, IF is 550, 2 times 550, 1600. We know that the constant rho is Fsi by Fs minus Fs by Fsi, which we want to use it for calculation of image frequency rejection ratio. So on substituting these values, we got the rho value, which is constant to be 2.8. So in the image frequency rejection ratio, which is rho square q square plus 1 under root, so therefore we have substituted this and we obtain 144.3 as the image frequency rejection ratio. Note down. Next problem. Note down. A receiver is tuned to 750 kHz, corresponding image frequency is 1750 kHz. Find FL, Laplace frequency, and image frequency rejection ratio. If two tuned amplifiers are having Q of 50 and Q of 70 are connected in cascade. Once again, read the problem. A receiver is tuned to 750 kHz. Corresponding image frequency is given. Find the Laplace frequency and the image frequency. Image frequency rejection ratio also. If two tuned amplifiers are having Q equal to 50 and 70 are connected in cascade for image frequency rejection, we are asked to calculate the image frequency and its rejection ratio and FL. So the image frequency, we know that given that incoming signal frequency is given, Fs is given to be 750. We know the image frequency is Fs plus 2IF, which is given to be 1750. It is given in the problem that the image frequency is 1750. So IF is being computed from this by substituting 1750 minus 750 by 2. So 1750 minus 750 by 2, which is an intermediate frequency of 500 kHz as obtained, which is FL minus Fs. So the FL is IF plus Fs. The Laplace oscillator frequency should be IF more than IF times than the signal frequency that is received. So the Laplace frequency should become 750 plus 500, that is the IF and the incoming signal, the received signal is at 1250. From the definition of image frequency rejection ratio, which is Fsi by Fs minus Fs by Fsi, we have computed it to be 1.9, and on substituting this value, we got it when two different Qs are being given. We have to take these two Qs into consideration in calculating the image frequency rejection. The image frequency rejection due to the first tuned circuit and the second tuned circuit. I will go back and show you the concept. Here, when more than two tuned circuits are being used in cascade with alpha 1 and alpha 2 are the gains of the tuned circuit, then we need to calculate the overall image frequency rejection ratio as a multiplication of any number of tuned circuits that are used. Why? Because this quantity is constant for all tuned circuits. That much as more number of tuned circuits are connected, more will be the image frequency rejection. With that amount, it will reject the image frequency quite strongly. Two tuned circuits are used. For the first tuned circuit with 50Q, for second tuned circuit with 70Q, so both are multiplied together. 12636.05 is the answer. As two tuned circuits are used, we need to use the same row which is common to both the tuned circuits. By using the Q value of first and second tuned circuits, we need to compute the image frequency rejection. More are the number of tuned circuits used for image frequency rejection, more will be the image frequency rejection ratio. Why? Because they are connected in cascade. Now the next problem. Note down, a receiver is tuned to 1 MHz and intermediate frequency is receiver is tuned means received signal is 1 MHz. Intermediate frequency IF is 455 and the Q is given to be 100. Find image frequency rejection ratio. Image frequency and its rejection ratio. If the receiver is tuned to 25 MHz. A receiver is first normally to be tuned, designed to be tuned to 1 MHz with an intermediate frequency of 455 kHz with a Q of 50. Find the image frequency rejection initially. Find its image frequency rejection ratio if it is tuned to 25 MHz. Okay. Now we will calculate the incoming signal is 1 MHz, 1000 kHz. Intermediate frequency is 455. We know the definition of image frequency is fs plus 2if, 1000 plus 2 times 455, all should be in kilohertz. 1910 kilohertz is the image frequency. So the constant rho is fsi by fs minus fs by fsi. We have calculated it to be 1.386. So the Q value which is given as 100. So image frequency rejection ratio is computed with the square root of rho square Q square plus 1, which is obtained to be 138.6. This is first part of the problem. Now the second part of the problem is find the image frequency rejection ratio if the receiver is tuned to not 1 megahertz, it is tuned to 25 megahertz. Next part of the problem. After you note it down, we will move on to the second part of the problem. It is routine. This part of the problem is routine. The second part is if it is tuned to a different frequency, that is 25 kilohertz. I'll move on to the next slide. So now the new incoming signal frequency to which the receiver is tuned to will be 25 megahertz. So therefore 25,000 kilohertz. The intermediate frequency is same 455 kilohertz. Now the new image frequency will be fsi plus, is equal to fs plus 2if. So therefore we need to calculate the new image frequency which is different from that of the previous frequency because it is tuned to a different signal. So in the similar fashion we need to calculate the image frequency rejection ratio. Before that this constant fsi by fs minus fs by fsi which is 0.072. The image frequency rejection ratio is 1 plus rho square q square, where you can find it to be less 7. So the same tuned circuit is tuned for image frequency rejection of 25 kilohertz 7.26. If it is tuned to 1 megahertz, the kind of image frequency rejection ratio is 138.6. So now the point to remember is, in the second case, if the incoming signal frequency is tuned to a very high frequency like 25 megahertz, image frequency rejection ratio becomes very small. For comfortable reconstruction of the signal, image frequency rejection ratio should be as high as possible. So more is the image frequency rejection, the receiver stability will be called as good, and then we need to always obtain more and more image frequency rejection. So that more is the incoming signal frequency to which you are tuning, you can't provide more image frequency rejection. That is the conclusion. Next problem. For the same problem, continue. Find the new value of IF required to get image rejection to be 138.6. For the same problem, for the above problem, find the new value of how much value of IF is required. Note down how much value of IF is required to get image frequency rejection ratio to be. What is image frequency rejection ratio? Alpha. To make alpha to be 138.6 and the receiver is tuned to 25 megahertz. So the receiver, the signal to which the receiver is tuned to is also given as 25 megahertz. FL is given. Fs is given 25 megahertz. So the given data is the desired image frequency rejection ratio is 138.6. The signal to which the receiver is tuned is 25,000 kilohertz or 25 megahertz. So we want to calculate the image frequency rejection ratio as square root of 1 plus rho square q square, which is given to be 138. It is given in the problem that it is image frequency rejection ratio is 138. If we solve for rho, we will get rho is equal to 1.385. Quality factor is given as 100 in the above question. The quality factor that is used is Q equal to 100. So only from this is the first part. In the second part, it is tuned to 25. In the third part, if I want image frequency rejection to be 138.6, what is that I want? If I by substituting Q as 100, we got the constant rho as 1.385. But the constant rho 1.385 is defined as FSI by FS minus FS by FSI. So out of these two, we have Fs with us, we have rho value with us, so therefore the image frequency we can calculate. if we solve this by substituting for Fs as 25,000 kilohertz, which is 25 megahertz, then the image frequency that is obtained to be 47.74 megahertz. But as per definition, what is the image frequency? Image frequency should be Fs plus 2IF. Substituting the values of Fs, okay, what is Fs? 25,000. So therefore, the IF value is obtained to be an intermediate frequency by substituting 25,000 here. 25,000 plus 2 times IF is equal to FSI, which is 47.74 megahertz. We get the intermediate frequency that is required to obtain an image frequency rejection ratio of 138. It is not practically obtainable frequency. This much amount of intermediate frequency, which is high for an AM receiver, please note it down as a remark. 11.37 is the new IF, which is required to get an image frequency rejection ratio of 138.6 for a received signal frequency of the same circuit with the 25 megahertz. Okay, I will move on to the next problem. So this problem is again a very important problem. Regularly in the GATE examination, these model problems are coming. I will conclude this problem and conclude this class. Still any more remaining problems are left over, we will discuss in the beginning of the tomorrow's class. Assume that the tuned amplifier is an Hartley oscillator and the incoming signal is tuned to an AM ranging from 550 kHz to 1650 kHz. Assume that the local oscillator frequency is greater than the signal frequency for case 1 and local oscillator frequency is less than the signal frequency for case 2. Intermediate frequency is IF is 500 kHz. The range of frequencies to which the receiver is supposed to be tuned to is Hartley oscillator and incoming signal is tuned to an AM range of 550 kHz to 1650. IF is 500. For case 1, the local oscillator frequency is more than the received signal frequency. For case 2, the local oscillator frequency is less than the received signal frequency. Find the ratio of C maximum to C minimum, that is in the tuned circuit present in the Hartley oscillator used for the tuning in the tuned amplifier. What is the maximum value of the capacitor that is to be used to that of the minimum value of the capacitor that is supposed to be used? Note down the given data. The problem is very clear. C maximum by C minimum we are asked to calculate. So the given data is the range of frequencies of the AM to which the receiver is supposed to be tuned is 550K to 1650 and the IF also given to be 500 kHz. For the Hartley oscillator, the oscillating frequency of any Hartley oscillator is resonant frequency of the Hartley oscillator is 1 by 2 pi root L1 plus L2. It makes of 2 inductors and a single capacitor. So therefore 1 by 2 pi root L1 plus L2 into C. If the incoming signal is tuned to minimum, let us assume that the incoming signal is first tuned to the minimum and then to the maximum. If it is tuned to minimum, it is tuned to 550 kHz and we consider case 1 that FL is greater than Fs. So in general also we know that the difference frequency between the local oscillator to signal frequency is IF. We also termed this as a minimum and maximum case because we tuned to minimum. So therefore the FL minimum, the minimum value of the local oscillator frequency that is desired is IF that is given to be 500 plus the signal frequency to which you have tuned. You have tuned to 550. So 550 plus 500 will be the local oscillator minimum. Okay. Now we consider case 1 now. 1050 is the minimum local oscillator frequency. If the incoming signal frequency which is tuned to the low that is 550, then the local oscillator frequency FL minimum that is the resonant frequency to which the Hartley oscillator also to be tuned to, that is FR minimum 1050. So by substituting this frequency as the frequency, Hartley oscillator of the incoming signal is tuned to this range of frequencies. The resonant frequency definition is this for the Hartley oscillator. Now this resonant frequency to which the local oscillator is being tuned to is equated to that equation by taking as the C value is in the denominator, we want to take it as maximum, right? So for FR minimum, C will be maximum. For FR maximum, C will be minimum. So this is what is the first one. 1 by 2 pi root L1 plus L2 into C maximum will be 1050, to which the tuned circuit is tuned to. Okay, tuned to the low. And if the incoming signal is tuned to the signal frequency which is maximum, in the problem the maximum frequency is given to be 1650. If 1650 is considered as Fs maximum, then again we want to calculate the intermediate frequency, which is defined as the difference between the local oscillator frequency and the tuned frequency to which the receiver is tuned. That is the signal frequency, which is 1650. So now FL should be equal to 1650 plus IF. So what is IF? IF is given in the problem as 500. The intermediate frequency is given as 500. Now substituting 500 as the IF and Fs maximum as 1650. The local oscillator new frequency when the signal is tuned to which the RF amplifier is or the receiver is tuned to a maximum, we want to also call it as the local oscillator maximum, which is 2150. Local oscillator minimum is 1050. Now also we want to substitute in the same Hartley oscillator frequency expression as this is maximum frequency to which the local oscillator is to be tuned, which is 2150. 1 by 2 pi root L1 plus L2 into C minimum should be equal to the highest frequency. We have two equations now, and we want to calculate the C minimum to C maximum. So one by the other, so by taking the equations 2 by 1, maximum to minimum can be obtained because it is in the denominator. Maximum to minimum can be obtained by taking 2 by 1. So maximum to minimum is 2050 by 1050. That is approximately equal to 4 whole square. Why? Because it is 2 pi get cancelled, root L1 plus L2 and root L1 plus L2 inside bracket may be squared, and we can minimize that. One by the other will give us the solution. So this we have done by taking the FL always greater than Fs case is considered, case 1. We have considered case 1. FL is greater than Fs. In case 2, if FL is less than Fs, quickly within 2-3 minutes we complete this part of the problem also and then conclude. So FL is less than Fs, then what we should do is we have to calculate Fs minus FL as the new IF. Why? Because we should not get any negative frequencies that are to be generated. So therefore we need to use Fs minus FL as the intermediate frequency. Why? Because earlier for case 1, what is the intermediate frequency? FL minus Fs as a general standard. And in the discussion also in the very beginning, in the first few slides, I have mentioned the point that if the frequency of the received signal is greater than the local oscillator frequency, then image frequency will also take new form. That part of it now we are discussing. For case 2, as the local oscillator frequency is less than the incoming signal frequency, so therefore as the local oscillator need to maintain a difference which is equal to IF, that is the standard rule. There is no hard and fast rule always that it should be always IF times more when compared to the incoming signal. As a case given, we can discuss it. So now the FL minimum should be Fs minimum, if FL is taken on right hand side and IF is taken on left hand side, Fs minus IF will become, um, uh, if this is FL minimum we want to take, so Fs minus IF. Fs minus IF is the FL minimum. Why? Because if you, first we will consider that we tune it to minimum. Fs minimum is 550. Fs maximum is 1650. Now we can remember 550 minus the IF that is given in the problem is 500. 550 minus 500, 50k. If the incoming signal is tuned to 550k, the Laplace frequency is tuned to FL minimum. That is the resonant frequency to which the Hart oscillator is tuned. Now 50 kHz is equal to 1 by 2 pi root L1 plus L2 to C max. Why? Because it is tuned to minimum frequency, capacitor will be maximum. So FR minimum, in the similar fashion as we have done in the previous part of the problem, we can calculate the Fs maximum. This is one relation. Another relation is Fs maximum we will consider 1650. The Fs minus Fi, why? Because of the log oscillator frequency and incoming signal frequency difference is to be calculated. FL maximum is 1650 minus 500. So therefore the 1150 we need to compute. So that 1150 will be the new log oscillator maximum frequency. That 1150 we will use as the resonant frequency maximum to which the Hartley oscillator is tuned. So that part we will equate to 1150. Similar equations we will get, whereas the capacitor value will be minimum. By dividing one with the other, C maximum to C minimum, we can obtain, and approximately it is fine. You can verify by using your calculators by substituting the numericals. So one can note down, verify whether approximately 500 is obtained or not. This is a case 2 where the log oscillator frequency is less than the signal frequency. So what is that we need to note down here is tuning of capacitor will be easy when FL is greater than Fs, so it is always preferred. When FL is greater than Fs, tuning will be easy, so that is the reason why we always prefer the Laplace frequency to be more when compared to the incoming RF signal frequency. Tuning of the capacitors becomes easy. So with this I conclude this class. Few more problems are left over. I will cover the leftover problems in the next class. Or if students are interested, you can note down this problem and conclude the class. I request the moderator to stop the telecast as it is 5:10. It is Sunday also. We can stop discussion for today. We will continue from tomorrow from this problem. Whatever the number of problems that are left over, 2 more problems are left over, we will discuss them. These are my references. Thank you very much. So those who are interested in noting down the problem, you can note down the problem. Yeah, conclude it, sir. Right, thank you.